Welcome to MathStat 341. I'm Professor Miller. This is lecture 10. The lecture for our guests will be online, so if you wanted to look at anything further or anything from the previous classes, happy to share that with you. Homework is available over there, solution keys for the next homework assignment. Hope to see some of you at some of the sporting events this week. The plan right now is to go to the football game. My daughter's hopefully going to have a play date with the coach's daughter.
Really?
Yes.
Oh, yeah.
So if you need anybody to throw out the first ball, oh wait, no, you don't do that.
I don't know if we do that.
Maybe the coin toss.
Exactly.
All right, so what I want to talk about today is a little bit more on independence, okay? Do you think it will matter if my daughter and the coach's daughter goes to the football game today? Do you think that will change, Saturday. Do you think that will change the chance of winning?
Give us some good luck.
You're generous. All right, do you think if I give a good lecture now that this will affect the outcome of the football game? No. Those should probably be independent events. Okay? Independent events is knowledge of one event gives you no information about knowledge of another. So the question is, how can we quantify this mathematically? We'll start with two events. So we had conditional probability. The probability of A given B was the probability of A and B divided by the probability of B. And then if the events are supposed to be independent, it's screaming at you what the probability of A given B should be. If A and B are independent, this should just be A. Not A, almost A. I'm sorry? No. The probability of A. Right. I mean, when you're saying A, you're essentially right. You just have to say the probability of A. So this is if they're independent. So if they're independent, the probability of A given B is the probability of A. We can rewrite this as the probability of A intersect B is the probability of A times the probability of B. That's a really nice way to think about things. The probability that both happens is the product of the probabilities. That's a wonderful rule. It then means you can figure out complicated situations from knowing simpler ones. We might have somebody outside. Yes. Are you trying to come to MathStat 341?
Yes.
Well,
so sorry.
No problem.
The code that they
Yes.
gave last year doesn't work.
Yes.
Yeah.
This is a high security facility. Some of the math we're doing has application. All right. So we've just started talking about independence. So the probability that A happens given B is the same as the probability of A if they're independent, so we can rewrite it this way. And then the question becomes, well, what if you had three events? A, B, and C independent. Is this the same as the probability of A intersects B intersects C is the probability of A, probability of B, probability of C? What do you think? Is that the right generalization?
I think you should include all pairs and combinations.
Ah, yes. So this is not enough. We need all pairs. For instance, if I want A, B, and C to all be independent, what if the probability of C is 0? Do you still want to be able to say A and B are independent? What if A and B are the same event? If A and B are the same event and C has 0 probability, then this equation will definitely be true, 0 equals 0. But do you really want to say A, and C are independent events when you've got one event repeated? So the correct definition is it's not enough for the probability of A intersects B intersects C to be the product of the probabilities. I need the probability of A intersects B is the product, and the probability of A intersects C is the product, and the probability of B intersects C is the product. And now you can imagine the joy of looking at 4 events and the exaltation that will happen when you get onto 5 events. And then you can keep thinking of greater and greater adjectives as you go further and further down. And you basically just say, look, whenever I take any finite subset of them, the product of the intersection is the product of the probabilities. And this will allow us to determine many events easily if we can calculate these. All right. So what I want to do now is I want to do a long problem on inclusion-exclusion. So this will take a while. But at the end of the day, the answer is going to involve a really good number of mathematics. So what number do you think might be involved? It's got to be a really good number. What are our candidates?
Pi.
Pi, that's a good candidate. It's not pi, so it is
E.
yes. So if you're doing a math problem and you get an E or a pi at the end of the day, you've done something right. You're looking at a good problem. And the Rook problem that I gave you, which was done with a student from last year, it does involve 1 over e squared. It's even better. It's not just e. So what I want to do now is I want to review inclusion-exclusion. So inclusion-exclusion. So the probability of A1 union AN is equal to the sum of the probability of AI, and so I goes from 1 to n, minus the sum 1 less than equal to I less than j less than equal to n of the probability of AI intersect AJ plus the sum 1 less than equal to I less than j less than k less than equal to n probability of AI intersect AJ intersect AK yada yada yada. At this point you can begin to see just how bad the notation is. If I want to do more and more terms, I'll have I, J, K, L. How do I do a general thing? You might do, instead of I, you might do I1, I1, I2, I1, I2, I3, doing it all the way up to IN. And that's a better way of writing it. Given that I don't want to overload you with notation, instead what I think I'm going to do is just use the I, J, K, and then just keep arguing that some things should be happening. Okay. Now, often, it's the same as the sum, well, I'll do it this way, as n choose 1, probability of A1, minus n choose 2, the probability of A1 intersect A2, plus n choose 3, probability of A1 intersect A2 intersect A3, minus dot dot dot. This holds if we're in the lucky situation where any event, just A1, A2, A3, has the same probability. Any intersection of exactly 2 has the same probability. Any intersection of 3 has exactly the same probability. So the example we're going to do is the example of derangements. Has anybody ever heard of mathematical derangements? Okay. Has anybody heard of other types of derangements? Okay. Yeah, my uncle, no. So let's do examples from graphs. Okay, graphs are wonderful. Let's see. Let's go over here. So if you were to graph the world, you might be interested in trade routes. What are some of the most important places in the world if you care about trade? For the flow of trade around the world.
China.
I'm sorry?
China.
Not China. I mean, in terms of producing things, yes. In terms of the flow.
Like the Panama.
The Panama Canal. What else?
Suez.
The Suez Canal. Okay. When we hear canal, this should be important, in terms of flow. So when you think of it, I will just do a really primitive, picture of world. And then, gotta make this a little bit better. Okay? Really not to scale. Okay? If you want to look, and you have boats, if you can't go through the Panama Canal, you've got to go all the way around. So what is the name of the cape down here? Cape of Good Horn, and the one down here is the Cape of Good Hope. Excellent. All right. So what you could do is you could actually draw a graph of all the places you can go to. And if you had key points here and you connect different places, just connecting all the different ways, you would have a lot of edges going to these places. These would be extremely important nodes. When you are looking at creating a network, you often hear about how well connected you are. You don't want certain critical systems to fail. So sometimes you might actually have redundancies, and you might have multiple connections. So for instance, it might be very important to have multiple connections between the White House and NORAD, so that if we have to launch a nuclear strike, oh crap, the phone line is down, oh well. You need to have a backup in a situation like that. In many things, however, we'll often have just one connection. And so what you want to do is you want to build a graph that's well connected so that if something goes down, you can reroute without too much trouble. If something goes wrong with the Panama Canal or the Suez Canal, it's going to have a major impact on world trade. So you want to build a graph with great connectivity. You can get from almost any vertex to almost any other vertex quickly. And if possible, you don't want to have choke points, where if this one point goes down, then the network crashes. And so there's a huge theory developed to trying to build such efficient graphs. And amazingly, a lot of advanced number theory enters into these calculations. And so some very strange things, the quadratic reciprocity actually comes to play in stuff like this. And so the question is, how do you build these graphs? So I'm trying to motivate why we care about derangements. So one idea is to create what's called bipartite graphs. So 1, 2, 3, 4, n. And then on the other side, we'll have the numbers 1, 2, 3, 4, all the way to n. And in the first iteration, I just connect everybody with their neighbor. And what I'm going to do is I'm going to make a graph that's d-regular, so everybody has exactly d neighbors. I'm going to connect everything on the left side to d things on the right, everything on the right to d things on the left. Nothing from left is connected to left, nothing from right is connected to right. And so what I want to do now is I want to choose another set of connections. Now, I could do a very highly structured one. I could do 1 goes to 2, 2 goes to 3, 3 goes to 4. And if I do something like that, I guarantee that I won't have a repeat. But I could have the possibility of small cycles, and if certain things go down, I could lose connectivity. So what we typically do is we choose a random permutation. So we permute the numbers 1 through n. And so we have 1, 2, ... n, and maybe when we permute them, we maybe get 4, 3, ... 1. And now we would connect 1 to 4, we would connect 2 to 3, and so on and so on. Imagine we had 5 and 5 down here. We've already connected 5 to 5. This means we would connect them again. Do we need that connection? It's a wasted connection. So the question is, if I have a permutation, because without loss of generality, I might as well assume my first connection is just the numbers 1 through n over here. When I choose another permutation, what's the probability I don't have the same thing twice in a row? So does this seem like now a well-motivated problem? I want to know what's the probability if I randomly permute these numbers that I don't have a number in the same place twice? How many ways are there to permute the numbers 1 through n? I'm sorry?
And choose one.
Not in choose one. That's the number of ways to choose one number. I want to permute them. I want to list them. I want to have a list of n numbers. N factorial. So there's n factorial arrangements. And that's about n to the n, e to the minus n, square root of 2 pi n. So if n is like 100, which is not a huge number, the number of permutations is tremendously large. We are not going to be able to brute force explore. Now what you could do is you could run some code and you could do some simulations. And you could say, let me just randomly construct 1,000,000 permutations of the numbers 1 to 100 and see how many of them have a number in the same spot. That's a very easy calculation to do. I strongly urge you to do something like that. And if you were to do that, you could get a sense of what the answer probably is. It is not a proof, but you're now doing some statistics and you can gain some confidence as to what the true answer happens to be. So we are going to calculate what is the probability that we have a number that's in the same spot. Or if that's too hard to calculate, what will we calculate instead? The complement, right. So if a problem is hard, sometimes the complement is easier, right? If the probability of winning is 20%, what's the probability of losing? 80%. So it's unclear initially which is going to be the easier thing to compute. I have deliberately not looked at this too carefully because it's going to be a lot of algebra. It's all in the book. Algebra can sometimes be boring. If I had to look at the lecture first and then give it again, it would just be too much. So we'll do the lecture live, try to find the algebra mistakes. So the first thing you always have to do in these inclusion-exclusion problems is you have to decide what are your events. So let's let AI be element I is permuted to I. So if I have 1, 2, 3, 4, 5, what movie has that as a code? Not Star Trek. Close. Cultural extra credit. What movie has the combination 1, 2, 3, 4, 5? For both an ear shield and luggage. So if I have that, no one gets the cultural extra credit today. Spaceballs. So would this have any AIs that would be a success? Is A2. Yeah, A2. So this would be A2, would be a success. A2 happens. What if I gave you instead, now what would be true?
A5 is true.
A5 is true as well. Anything else?
A4.
And A4. And A2 intersect A4 would be true. Right? Because I have 2 in the same spot and 4 in the same spot. We would also have A2 intersect A5. We would also have A4 intersect A5. And we would also have A2 intersect A4 intersect A5. All of those would happen. No. The clock is ticking. So rather than always write this, we could introduce notation. Call this A24. Call this A25. Call this A45. Call this A245. If it gets confusing, is this A245 or A245? If you're ever not sure, you just put in commas. And that's a little bit faster to write. So these events would all happen for the string 32145. And anything else would not happen. Okay? So these are our events. So AI is the event that element I is permuted to I. Okay? So we want to calculate what is the probability that at least one element is returned to where it starts. So probability at least one is unmoved. How would we call that probability in terms of these A's? What event would it be? So it should involve A1, A2, A3. How does it involve all these sets A's?
What would be the complement?
Well, so we want the probability that at least one happens. So if it's the complement, so the complement of A, are you trying to, how do I combine them? How do I combine the sets A? It's the union. It's the probability A1 union A2 union AN. That's the probability that at least one of them happens. And now we just need to calculate this probability. So this is going to be the probability n choose 1, the probability of A1. Right? Because A1 has the same probability as A2 has the same probability as A3. Minus n choose 2, the probability of A1, 2, because they all have the same probability. Plus n choose 3, probability A1, 2, 3, and so on and so on and so on. So we're in the very fortunate situation where all of these events are essentially the same. Because if I look at the event that the first one is unchanged, that's the same as the third one is unchanged. I just change my labels of things. So what is n choose 1? It's n factorial over n minus 1 factorial 1 factorial. And now what's the probability of A1? The probability that when I shuffle n numbers, the first number doesn't move. So it's probably, I'm going to write it as a fraction. How many shuffles are there? How many ways are there to permute the n numbers? N factorial. So the denominator is n factorial. I have n factorial ways to permute things. How many ways can I permute them and have the first one unchanged? So what would that be? The first one has to go to 1. Yes?
Would it be n minus 1?
Yeah, it would just be n minus 1 factorial. The first one is unchanged and everything else moves. Now, if you look at this, do you hear what it's telling you to do? I'm sorry?
Cross cancel.
Yeah, I thought you said for a second it's loud. It is extremely loud, yes. Let's look at the next term, n choose 2. That would be n factorial over n minus 2 factorial 2 factorial. Now what's the probability of A1, 2? The probability that 1 and 2 are both unchanged. Well, I divide by n factorial. Now that I fix the first 2, the last n minus 2 can be permuted freely, and it's just n minus 2 factorial. Okay? We'll do one more term. N choose 3 is n factorial over n minus 3 factorial 3 factorial. And now I want the first 3 things to be fixed, so I can permute the last n minus 3 however I want, so it'll just be n minus 3 factorial. And as has been remarked, cross cancel. I don't know why I'm not writing the 1 factorial first, which would have made the cross canceling easier. Kind of fun and cathartic. Massive death, massive cancellation. We get 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial. And we go to plus or minus 1 over n factorial. I could figure out if it's a plus or minus 1, I don't care. Does this look like anything you've seen before? What does this kind of remind you of? I'm sorry? Yeah, for what? For E, right? So this is where you play algebra. E to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial. So this is where you have to do algebra. And so there are many things I like in the world. One of them is Rubik's Cubes. Oh, yes, good. Have I shown Rubik's Cubes in this class yet? Okay. So if anybody wants to learn, it takes about an hour to learn how to do a 2x2 cube.
But that one's...
Okay, so this is a standard Rubik's Cube. It's nice. It actually turns extremely well. For years, these cubes were illegal in competitions because if you look straight down, you can see this is the yellow-green side, and somebody looking like this could get a little extra information. I am not even close to good enough where that would matter, and they finally said, screw it. If people can gain information from that, let them use it. This one looks somewhat similar, but if I try to turn the red side, it doesn't quite work. And so I like to use these to showcase the power of looking at algebra the right way. If you look at things the right way, it becomes very easy. So my daughter had one like this in her 3rd grade class that they gave to me to solve because they couldn't figure it out. It was a little bit different. They all had the same color on each side, and the different sides were different sizes. So they used size rather than color. The solution is, this clearly looks like a side. I can turn this yellow, very, well, okay. In theory, I can turn the yellow very easily, right? I can turn the white very easily, but I can't turn the red easily at all. It doesn't work. The solution is you hold it at a 45-degree angle, and now that's one of your sides. The side is half red, half blue. This side over here is another one. It's the blue-orange side. And if you hold it like this at a 45-degree angle, it's essentially the same as this one. The only change is because this is not a square, it's a rectangle, it's solving a Rubik's Cube with a picture on it. And it's possible to solve a Rubik's Cube and have the centers rotated. You won't notice it if it's on a cube like this, because if this center square is rotated 90 degrees, you're not seeing it. But if there's a picture, it's like, why is that upside down? And this does happen. When I was at Princeton, they were building the new campus center. Someone had to say, didn't you put like some of the Princeton logo upside down in the big glass shield on the library, campus center? And so they actually had built some of it upside down. There was an art museum in Italy where they had a modern art exhibit, and one of the graduate students who was going through it asked the curators, your picture over here is 3 panes. The middle pane is flipped from what's in the book. Which one is right? And given that it was modern art, no one knew, which was quite amusing. Now, in terms of derangement, 2 out of 3 were the same on that one. But one was definitely different. Looking at algebra the right way is extremely important. Let's look at this. What do you think you might want to take for x? So this is the same as 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial. The hardest part is always sniffing out how to do the algebra. Any thoughts what might be a good thing to take for x? Yes?
1.
That's it.
All the
Oh, sorry. I put in some mistakes. Sorry. I'll let you correct that now that I've actually written the correct formula on the board. Yes, -1. Yes. I just had an inkling where things were going. I'm so excited to get there. If we take -1, e to the -1 is 1 minus 1 plus -1 squared is 1, so it's 1 over 2 factorial, minus, because -1 cubed, 1 over 3 factorial, plus 1 over 4 factorial, minus ... Does that look a lot like what we have? What's the difference?
first check.
Yeah, so what we can say is if we did -1 plus e to the -1, that'd be -1. So if we add that, the -1 would cancel that 1 over here, right? And then we would have -1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus ... And now, this looks very close to what we have. It's off by a minus sign. So if we now multiply through by minus sign, we get 1 minus 1 over e is 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus ... So we have calculated the probability that an element is returned, that at least one element is returned, is 1 minus 1 over e. What's the probability that no element is returned?
1 over e.
Yeah, isn't this wonderful? We're trying to find a complementary probability, and what's the answer we get? 1 minus 1 over e. Yes?
So, but I guess for this one, like, there's only finitely many.
Correct.
But then it's
So in the limit as n goes to infinity, the probability converges to this. So if you only do a finite n, it is not the answer. And in fact, you can even say how close you are to the answer. But as n gets larger and larger and larger, you have, not only does n factorial decay rapidly, when you look at 1 over n factorial, but you're alternating sign. So you're getting cancellation from sign as well. So it's going to converge really rapidly. And so in the limit, as n goes to infinity, the probability that no element is fixed converges to 1 over e. And the application of this is you can use this idea to just choose random permutations, and the probability that the permutations will align is going to be about 1 over e. So that means that just choose another one, and you'll have a reasonable probability that if you just choose 2 permutations, they're not going to align anyway. You're not going to have to wait too long, even if n is very large. There are other problems that we will see later in the semester that are related to 1 over e. It's amazing how often this turns up. I will keep it secret for now, so that it will be a surprise when it shows up later. I will say that it has implications to how you choose to spend the rest of your life. One of my former students has decided to embrace this, and it has not worked out for him. And so there are sometimes issues with applying mathematics.
So it is 1 minus, I mean, it's -1 plus e to the -1 power, a reasonable approximation.
Say that again?
Is that a reasonable approximation for a finite number of terms?
Oh, in terms of how many terms we go to?
No, if you just use e to the -1 minus 1, or the complement, is that a reasonable approximation?
For the probability that you have something that has nothing that's kept fixed?
Sure.
Well, because are you saying like if we stop after 4 terms, what's the error?
Yes.
So if we stopped after 1 over 4 terms, the next term is of size 1 over 5 factorial, which is 120. So with 5 terms, we would be off by a little bit less than 1%. Now you do subtract off 1 over 6 factorial, so you know when you have the 1 over 5 factorial, that's a little bit of an overestimate for the error. So if you go a little bit further, if you go up to 10 terms, then you have 10 factorial, and then it's really a good approximation. But 4 terms is enough to already get to within 1%.
All right. Thank you.
Okay. So this is a great example of the power of inclusion-exclusion. There are a lot of different places where you can apply inclusion-exclusion. One of my favorite examples what is Intel? Chip maker. Is there anybody here who has not heard of Intel? Their marketing department will be thrilled. Okay? First thing is you always want recognition. But sometimes you might not. Anybody remember what a Pentium is?
No.
They used to call their computers the 286, the 386, the 486 for their chips. And then instead of calling it the 586, they called it the Pentium. Now, have you ever heard of the Pentium bug? Excellent, I see a couple of people. So those of you who have not heard of the Pentium bug, their marketing department is even happier. So Intel launched this big campaign that the most important part of your computer is the processor. What a surprise, right? That the people who make the processor say that this is the most important part of the computer. And so the mathematician nicely was looking at the sum of the reciprocals of the twin primes. So he was looking at 1/3 plus 1/5 plus 1/7, because those are still twin primes, plus 1 over 11, plus 1 over 13, plus 1 over 17, plus 1 over 19. I know at this point it looks like almost everything is working. But then 23 is prime, but 25 is not prime. 27 is not prime, 29 is prime, 31 is prime. These would be the next terms. And it was proven by Brun that this sum converges. It was a huge disappointment. Because people have been trying for millennia to prove that there are infinitely many twin primes. If the sum diverged, what would that tell you about the number of twin primes? Infinitely many. If it's only finitely many twin primes, the sum can't diverge. So the hope was to show that the sum was infinity. Brun actually bounded the sum. And he used inclusion-exclusion, which is why I'm mentioning it now. This is one of the best applications I know of inclusion-exclusion. So because it converges, people are curious, well, what does it converge to? And the series converges slowly. And so nicely was trying to get a better result than previous people. And so he was calculating the sum of the reciprocals of the twin primes on his new Pentium, and it wasn't matching what he got on his old 486. It was that strange, you know. And looking at things more carefully, it turns out that the Intel processor was having a little bit of trouble with division. Most of the time it was fine, but like every billion or so would be off a little bit. Intel knew about the problem. You know, how likely is it that someone's going to need to do like 1 billion consecutive digits of divisions and be accurate to this level? It's fine, ship it. Well, once this was discovered, there was panic and pandemonium. You know, people wanted processes that divided properly. And people were worried, what if I, no, you're doing a little Excel spreadsheet for your son or daughter's Little League team. I don't think you're doing 1 billion divisions. I don't think you need 12 digits of accuracy. You're not sending someone to the moon. Your computer is fine. But what do you think Intel had to do? Give them all new, not computers, but new processors. It was the processor recall. And so this cost, I think, hundreds of millions of dollars to Intel. Plus you got some wonderful commercials from their competitors who said, we agree with Intel that the processor is the most important part. Ours can divide. And so one great application of pure mathematics is a test. So anybody here who's doing statistics, you can't do statistics in the 21st century without doing something on a computer, without doing some type of coding. How much do you trust your computer? So I want you to be warned, I want you to be thinking. Okay? Now, should you have some faith? Yes, I mean, if you have to spend your entire life checking everything, you're not going to be able to do anything new. But be careful. I will risk another cultural extra credit. First one to give me this will get the extra credit. I find your lack of faith disturbing. Thank you. Feel a little bit better now. And he is clumsy as he is. All right. So the last thing I want to do is I want to talk about multinomial coefficients. What do you think multinomial coefficients generalize? Binomial, okay? I'm going to choose two great states, the great state of Iowa and the great state of Mississippi. Mississippi is probably the hardest state to spell. How do you spell it? Yes? The answer is?
M-I-S-S-I-S-S-I-P-P-I.
No.
Oh, what?
Old joke. Mississippi is a hard state to spell. How do you spell it?
Oh.
Old joke.
What?
Let's play a game of permuting the letters of the state. Now, it'll be interesting if this actually helps or hurts with our recruiting efforts.
You permute the letters of the state, not Mississippi.
Yeah, we'll permute the letters of Mississippi and the letters of Iowa. So this is being extremely clear. Now, we will also assume that you have to use all the letters. How many ways are there to permute the letters of Iowa and get distinct words?
Well, 4 factorial, but those won't be real words. So
They may not be English words, right? Wire. Wonderful expression. I think that's what you say when you find out that your function is thrice differentiable. So you can make up, okay. What about Mississippi? How many ways are there to permute the letters of Mississippi and get distinct words? What's the problem?
There's repeated letters.
Yeah, there's repeated letters. Wouldn't it be much better if you spelled Mississippi M-I-S-T-J-U-V K-P-Q, can't use M, so M. So if I spelled Mississippi like that, wouldn't it be a lot easier? Actually, it sounds like a job for Arkansas in terms of how things are spelled and pronounced. But so if I did it like that, would the problem be easy? How many ways are there to arrange the state? 11 factorial. So what we want to do is essentially convert from Mississippi to the state. What we're going to do is we're going to change S, but rather than calling the first SS, we're going to call it S1. And what do you think we should name the second S? S2. Then this will be I1, I2, S3, S4, I2, P1, P2, and, all right, so this should be I3, and then this is I4. So there are 11 factorial ways to arrange the letters of Mississippi. But in the 11 factorial ways, for the 4 I's, can we distinguish between an I1, I2, I3, I4? What do I have to divide by? 4 factorial. What do I have to divide by next for the S's?
4 factorial.
For the P's?
2 factorial.
Anything else? What if you really like being pedantic?
1 factorial.
How many times?
For the M.
For the M. We only have 1 M. And what's nice now is 4 plus 4 plus 2 plus 1 is 11. So I like it always when the bottom sums to the same as the top. I've accounted for everything. You know, this is the same if I want to choose from 10 people, 3 people to get something special. Maybe I want to continue and choose 7 people to exclude. You know, sometimes it's nice to throw in that extra factor. So when you look at what's going on here, how could I really view the word Iowa? It's 4 factorial divided by 1 factorial, 1 factorial, 1 factorial, 1 factorial, which is almost the worst thing you can see in mathematics. The only thing I've seen that is worth is the uppercase C from Greek. So the one that's often done is xi divided by xi, and you take the complex conjugate of the numerator. That's probably the worst thing you could have to pass.
Have you seen that?
Yes. Well, I mean, only by people trying to be nasty. No. The one I came up with was this. How do you read that? Sorry? Z naught, not, not. So you want to think about how you write things. N-A-U-G-H-T for the last one. So what's a multinomial coefficient? So if I have x plus y to the n, this is the sum n choose k, x to the k, y to the n minus k. And I have k goes from 0 to n. I could look at this another way, and this is going back to the Rubik's Cube. What do I want you to get out of today's lecture? The power of looking at things many different ways. I could look at this as a sum, maybe k1, k2 go from 0 to n, k1 plus k2 equals n. And now, I would have x to the k1, y to the k2. And I would have n factorial over k1 factorial, k2 factorial. Well, given that k1 plus k2 equals n, this tells me that k2 is just n minus k1. This is just the same as this, except now I'm using k1 rather than a k. There's really no difference. So what I'm saying is x plus y to the n has this beautiful representation. We can now look at x plus y plus z. And when you expand it out, what do you think you're going to get? So what would be your conjecture? K1 factorial, K2 factorial, K3 factorial, x to the K1, y to the K2, z to the K3. You would have a sum K1, K2, K3 go from 0 to n, K1 plus K2 plus K3 equals n. That's a very reasonable conjecture. And given that these are called the multinomial coefficients, and they're supposed to be generalizing the binomial coefficients, this is a great way to do it. Have we talked about parentheses and grouping in terms of like the derivative rule of a sum for calculus? That the derivative of a sum is the sum of the derivatives. But you only prove that in calculus if you have a finite sum. And you can use mathematical induction. You can say if you have finitely many terms, the derivative of a sum is the sum of the derivatives. And the way the proof works, just make sure this is in focus, is let's say we know that the derivative of a sum is the sum of the derivatives. If I give you a sum of 3 functions now, I could write f and g together and then h and take the derivative. And then since I know the derivative of a sum of 2 things is the sum of the 2 derivatives, it would be the derivative of f plus g plus the derivative of h. And then inside here, I could get f prime plus g prime plus h prime. And now I can drop the parentheses. And this proves if you know the derivative of a sum of 2 functions is the sum of the 2 derivatives, then the derivative of a sum of 3 functions, it does not hold that that you always have the derivative of an infinite sum is the infinite sum of the derivatives. You need real analysis and you need conditions on when you can do that. But in many situations, you can argue like this. Why is this useful? Well, when we were looking at x plus y plus z to the n, you can view this as x plus y plus z to the n. And then when you expand this, what can we use to expand this? So what theorem do we use to expand this? The binomial. We no longer have a trinomial, we're back to a binomial. So this would then just be the sum, say k goes from 0 to n of x plus, of n choose k x plus y to the k, z to the n minus k. Yes?
Was there meant to be an n exponent on the x plus y list?
Yes, there was. Yes. Thank you. Now, what do we do? Yes?
Can you replace x plus y to the k with using the binomial?
Yeah, we just use the binomial theorem again. And so we would now have, a sum k goes from 0 to n, a sum L goes from 0, it can go at most k, and we would have n choose k, and we would have k choose L, and we would have x to the L, y to the k minus L, z to the n minus k. And now, here's the lovely algebra. You get n factorial over k factorial, n minus k factorial. I can't write things in the right order today. I keep doing it in the wrong order. Well. And then over here, the k factorial over L factorial, k minus L factorial. The k factorials cancel, and you get n factorial over L factorial, k minus L factorial, n minus k factorial. That's just the multinomial coefficient, n choose L, k minus L, n minus k. And that is the proof of where the multinomial coefficients come from when I have a trinomial. What should I do next? Building on our success with trinomials, 4 and higher, right? You don't want to see it, I don't want to do it, we're all on the same page. Okay? It runs through similarly. Okay? It's a nice induction problem. And it shows you that there's going to be relations between multinomial coefficients and products of binomial coefficients. And these coefficients are going to be extremely useful for us in terms of trying to calculate probabilities of events. So multinomial coefficients would be, I want to look at all these different ways, and I have these additional constraints. So it turns out we can handle these additional constraints without too much trouble. We can generalize the binomial theorem without too much trouble. All right. Any other questions on this? All right, so this is a good place to stop.